Log on, tune in, find out. Another good idea from Cambridge.
From Zurich, and who will speak about the approximation by plane waves.
Thank you for the introduction, and thank you to the organizer for the possibility of being here this week. I'm going to talk about my PhD project. I'm working on this project with Ralph Meyer, my advisor in Zurich, and with Ilaria Perugia in Pavia. You have already seen an introduction to my talk on Monday by Ilaria. We start from homogeneous Helmholtz equation, standard Helmholtz equation. You have a domain in 2 or 3D. You put some reasonable boundary condition, and we know a lot of good properties of this PDE. But we also know that if you want to discretize, if the wave number is large, means we have highly oscillatory solution. If you want to discretize, it's not that easy. There are not only you need a lot of degrees of freedom to resolve the oscillations inside the domain, but there are also some special phenomena like the numerical dispersion or the pollution effect that affect your numerical solution. This means standard finite elements are not enough. You need some smarter idea. One of the possible ideas is to use a Trefts method. What does it mean? We have seen on Monday, I repeat, a Trefts method is a method where every trial and test function inside one element is solution of the PDE we are dealing with. Means inside each triangle of our mesh, or tetrahedron, or whatever you want to use, all the functions we are using are solution of Helmholtz. Which kind of discrete function can we use? Most of the method of the Trefts method for Helmholtz available are use plane wave basis functions, where with plane wave I mean just the standard, the simple solution of the Helmholtz that is constant on the planes and is oscillating in the orthogonal direction. Or there are some methods that are using circular waves in 2D, spherical waves in 3D, some corner wave near the corner of the domain, or there are methods that are using more exotic basis function, singular solution, or something even more complicated. We know when we studied the finite elements that in order to prove the convergence of a finite element method, usually we prove a quasi-optimality estimate. That means we say the error committed by our method is very close to the best approximation error allowed by our space, and then we use a best approximation estimate that says if we have our finite dimensional space, this space is able to approximate the exact solution with a certain small error. And usually we are using polynomial basis, so we can use Brembo-Hilbert in H or many other results. If you want to use, for instance, plane waves, we don't have all these nice results available. We have to use something, we have to prove something a bit new. This is the kind of estimates we want to prove. If we have a solution of our PDE, a solution of Helmholtz, inside D, that is one element of our mesh with diameter h, we want to say there exists a linear combination of p plane waves with fixed direction decay that approximate our solution u in some norms j with an error that is going to 0 when we restrict the domain, when this is h convergence, when the domain is getting smaller, or when we increase the number of the plane waves, that is p convergence. With polynomials, we are used to raise the degree of the polynomial. Here we don't have a degree. The p convergence with plane waves means just adding more and more direction of plane waves. And we want to prove something like this. There are not many results available basically two, one by Cessenin-Depré and one by Meleng. They are both quite strong results, they're quite deep, but they are not enough. They are not enough general and not sharp. So we want to say something more. What we want to prove is some best approximation estimate for plane waves and some estimate for the circular or spherical waves. We want estimate in H and P in 2 and 3 dimensions, and we want the constant in front of each bound to be explicit in the wave number omega. The good news is that we can prove all these things. The bad news is that in the case of the P estimate in 3 dimensions is not really what we would like to have. There is a small detail that is not that small maybe, that is not completely satisfactory. So you have to follow these 3 steps. First of all, a special tool called Vequa theory. Then we will prove some approximation estimate by generalized harmonic polynomials, and then by plane waves. And then, if there is some time, I would like to talk a bit about the same problem for the Maxwell equations. So, Vequa theory. We have a domain D that represents one element of our mesh, star-shaped, and we define star-shaped with respect to the origin, and we define 2 functions, M1 and M2 function on the domain time a parameter space 0, 1. And these functions are just simple functions defined using the Bessel function J1. The first one is very oscillatory, and the second one is increasing exponentially because we have Bessel function of imaginary argument. We use these 2 functions to define 2 operators that are acting from the space of complex valued continuous function on the domain to itself. And these integral operators are very easy, well defined. It's quite interesting to see a bit, before to see why we are using these operators, to see the history of these 2 operators. Ilya Vequa was a Georgian mathematician. He wrote a few papers where he defined these operators for the Helmholtz equation in n dimensions without giving any proof in 1942. After a few years, he wrote a book where he generalized this operator from Helmholtz to much more general elliptic equations, but only in 2 dimensions. And he wrote only 1 page about the special case of Helmholtz that can be generalized to higher dimensions. And this book was written in Russian. After 10 years, Peter Henrici wrote a sort of summary of the book of Vequa, a very nice summary, but he forgot the page about the n-dimensional version for Helmholtz. After last year, the book was translated in English, but all the people who used Vequa theory just probably read the summary of Henrici. Nobody read the original work of Vequa. And so the n-dimensional version was forgotten. And many people, like David Colton, Robert Gilbert, and so on, tried to generalize the Vequa operators to higher dimensions, but they didn't know that this was already available in the first paper by Vequa, 30 years before. But this was already there. Why do we care about these operators? We can prove a few things about with this. First of all, something very simple. One operator is the inverse of the other one. The real important thing is this one. If you have a solution of Helmholtz equation with wave number omega, the Vequa transform of this solution is an harmonic function. And this is the reason why we want to use these operators. We have our Helmholtz problem, some oscillatory problem. We can transform into something much simpler, some harmonic problem. We know there are a lot of results about harmonic functions, and we can try to deal with our problem in the harmonic setting, and then return back with the other operator, with the inverse operator, to the Helmholtz setting. And in particular, when we are in the harmonic setting, we don't have the wave number, we don't have oscillations. It's quite a different problem. In order to go back and forth with these operators, we need to prove some continuity, and we can prove continuity in any Sobolev norms with the constant that is explicit in the wave number. In particular, it depends on the product of the wave number times the size of the domain, the diameter h of the domain. And we have to use weighted Sobolev norm, weighted with the wave number in some reasonable way. Now, with this operator, we can prove some approximation estimate. We start with our solution of the Helmholtz equation, so inside our domain with some bounded Sobolev regularity. We apply the operator V2, and we obtain an harmonic function. Harmonic function can be approximated by harmonic polynomials, or at least we can hope that is possible. Then we apply again the other operator, V1, and we recover the original function U. This function can be approximated by the image under V1 of these harmonic polynomials that are approximating V2 of U. And the image under this integral operator of the harmonic polynomials are called generalized harmonic polynomials. These are not strange functions, these are just the standard Fourier-Bessel functions, or circular waves in 2D, spherical waves in 3 dimensions, are just Bessel function in the radial direction times Fourier basis in the radial direction in 2D, or spherical harmonics times spherical Bessel functions in 3D. They are the solution of the Helmholtz equation in spherical coordinates. So, if we are interested in the H convergence, we can work like this. We say the best approximation of our solution U, our Helmholtz solution U, by generalized harmonic polynomials of degree at most L is bounded by the same problem translated into the harmonic setting, thanks to the continuity of V1. The approximation of this harmonic function V2 of U by harmonic polynomials, if you are interested in the H convergence, is given by the Brembo-Hilbert theorem. If you have an harmonic function and you apply the Brembo-Hilbert theorem, the polynomial you get is harmonic. So can be plugged inside here, and you have some more the standard order of convergence of Brembo-Hilbert. And using the continuity of V2, we recover the norm of U on the right-hand side. So we have already an H estimate in for spherical waves. Very easy, depends only on the continuity of the two wave operators and a standard tool like Brembo-Hilbert. But we want some convergence in L, the degree of the harmonic polynomials, or the generalized harmonic polynomials. In 2D, this result is already available thanks to Marcus Mehring. I forgot to say at the beginning, the general framework we are using for the this approximation is not new. Actually, it comes from the work of Mehring. That was he did more or less the same thing for a more general problem, more general elliptic equation, but only in 2 dimensions. But the global structure of the theory is from his PhD thesis. And he proved this result in 2 dimensions. If the order of convergence in the degree of the harmonic polynomial is given by the difference between the indices of the Sobolev norm, k plus 1 minus j. Remember here k plus 1 and j are the indices of the Sobolev norm, multiplied by a parameter lambda that is given by the reentrant corner of the domain. It means we have a nice algebraic convergence, like for standard polynomial. The only difference from a standard polynomial is this logarithm term, so not a big difference. And this is sharp. There are some numerical tests that show this is sharp. But we want to generalize to higher dimensions, so we have to look into the proof of this. And we see that this heavily relies on complex analysis. In 2D, we can transform our domain using conformal mappings into the unit ball. We have harmonic function. That means we're basically using holomorphic function. Holomorphic function can be interpolated on a special point on the disk by complex polynomials, and the complex polynomials are harmonic for free. So we have a lot of tools that are given almost for free in 2 dimensions, and they don't carry over to three or more dimensions. Of course, then there are much more things in the proof of Mehring. It's quite complicated, but these are the things that are working only in 2 dimensions. So in 3D, you have to use a more complicated result by Bagby, Bose, and Levenberg that gives exponential order of approximation in compact subset for functions that can be extended outside these compact sets. And then using some special technique, we can recover an algebraic order of convergence in Sobolev norm in the same setting we've seen before. And it seems we have the same result more or less as before. We have an algebraic order of convergence in L with the order that is given by the difference between the Sobolev indices, k plus 1 minus j, times a parameter lambda that depends only on the shape of the domain. The problem here is in this lambda. In 2D, we know, thanks to Mehring, that lambda is the reentrant corner of the domain. If the domain is convex, for instance, lambda is 1 in 2D. In 3D, we know only that lambda is positive. We are not able to give a nice bound on this parameter. And this is the main gap in the theory, because this lambda is the parameter that gives the actual order of convergence. And we would like to say, if the domain is a nice domain, is convex, for instance, lambda is 1 or close to 1, but we're still not able to do it. And of course, both in 2 or 3 dimensions, if the solution can be extended outside the domain, we have an exponential order of convergence. But here we want to prove some convergence also for a solution with a singularity on the boundary of the domain. So we want to use this algebraic convergence. So we put all the results together. We have the harmonic orders of convergence. We apply the equicontinuity, and we have the orders of convergence for the approximation by generalized polynomial approximation of any solution of Maxwell, of Helmholtz. And we have algebraic order in H, algebraic order in L, and we know this parameter lambda. And this is the best approximation estimate you can directly plug in the analysis of your Treff's method that is using Fourier Bessel function, for instance. But now we want to prove some estimate for plane waves. What is the connection between plane wave and circular waves? It's called Jacobi-Unger expansion. It's a very well-known function from a spatial function theory. You can find it on Wikipedia. That gives one plane wave is equal to infinite sum of generalized harmonic polynomials. It's not exactly what we want the other way around. We want to say our generalized polynomial can be expanded as plane waves. So we have, in some sense, to invert this expression. You see, in 2D, we write a generalized polynomial minus linear combination of 2q plus 1 plane waves. We use this index from minus q to q because it's convenient. And if we write a generalized polynomial and if we expand the plane wave with Jacobi-Unger, we see the dependence on x is the same on the two sides. So we can have an approximation if this alpha k, this coefficient of the plane wave, can match with all this term, with this sum, can match this coefficient of the generalized polynomial AL. And this is possible if the alpha k are solution of a linear system given by this matrix. And since this matrix is a van der Monde matrix, is always invertible, and we can give a nice bound on the norm of the inverse of this matrix, and even if the plane waves are not equispaced, the direction of the plane waves are not equispaced, we can control the different error we have when two directions are getting closer, or if we choose a string, we have a string choice of the directions. So this gives best approximation estimate for a generalized harmonic polynomial by 2q plus 1 plane waves. But there is another interesting thing we can see from this procedure, is that the coefficient of the approximating linear combination of plane waves are given by the solution of a linear system whose matrix is independent of the wave number and is well conditioned. In the case when the directions are equispaced, the condition number of this matrix is 1. If they are not equispaced, it's not huge. This means if you are able to approximate your solution with generalized harmonic polynomials, you can approximate for free with plane waves. I don't know if this is useful, but at least it's quite interesting, because many times, you see, it's quite difficult to find the plane wave bases are very ill-conditioned, so it's difficult to find approximation. But approximation, the step from generalized harmonic polynomials to plane waves can be done very easily with this linear system that takes care only on the angular dependence. So we want to do the same in 3D, and the matrix we have to of the system we have to solve now is given by spherical harmonics. So in general, it's not even invertible, and we would like to give a bound on the inverse of on the norm of the inverse. So we need to be a bit more careful. We see that there exists an optimal choice of directions such that the norm of the inverse is growing a very nice way, it's just linear in the number of the plane waves. And we can also see that this optimal choice corresponds to the so-called extremal system introduced by Sloan and Womersley that are used for the quadrature on S2, on the sphere. This means we don't have to compute, we can just connect to their website, download the optimal direction, and we have our optimal choice of direction for our plane waves. But it's possible to do also something simpler. If you choose some heuristic, some almost equispaced direction on the sphere, you see it works very fine from the numerics. So it's not so important to have the optimal choice of the direction. And this way we get the same result as we had in 2D, more or less, just that it doesn't work for any choice of the direction, but only for some good choice that is not difficult to find. So now we just have to do a sort of triangle inequality. We have our solution of Helmholtz. We can approximate by generalized harmonic polynomials using the equatheory. Now we can approximate the generalized polynomial by plane waves, big triangle inequality, and we obtain approximation for a generic solution of Helmholtz by linear combination of p plane waves. And this gives an algebraic order of convergence in H and in Q, where Q now is not exactly the number of directions, but is a sort of degree of the space of the plane waves. If we, like with polynomials, we have a degree and we have a number of degrees of freedom. In this case, Q represents the degree and P represents the number of degrees of freedom, the number of plane waves we are using. And they are linked in this way. P corresponds to the number of degrees of the dimension of the space of harmonic polynomials up to degree Q in 2 or 3 dimensions. So it's like if you are using only harmonic polynomials. It means we are saving some degrees of freedom respect to the general polynomial approximation. And so this is the estimate we have. What can be done? We would like to have an explicit order in P in 3D, because remember here we have this parameter lambda that in 2D is known, but in 3D we don't know anything. We would like to generalize this approach to the Maxwell equations, and we want to prove some adaptivity estimate. So far, all the estimates with the plane waves were something like, given this direction of the plane waves, there is a linear combination of these plane waves that gives a nice error. But we would like to say there is a choice of direction and the choice of coefficient that gives a better bound, a better approximation bound, without fixing a priori the direction. This is a non-linear approximation instead of linear, because we want to free also the choice of the direction, not only the coefficients. Do we have time for Maxwell? Very fast, Maxwell. Okay, with Maxwell I mean just a curl equation, the simplest possible version of Maxwell. We have we know that it is equivalent to having Helmholtz in each component and the divergence-free constraint. The first idea we can have for the approximation of this solution with plane waves is just to use the Helmholtz approach. Fix p direction. For each direction we fix 3 vector plane waves, direction of propagation I mean, and we obtain the same approximation as we have for Helmholtz, because each component is solution of Helmholtz. But this is not a Tref's valid approach, because this way, if you choose general plane waves, vector plane waves, these are not divergence-free. You have to choose the plane waves with propagating direction with an amplitude vector orthogonal to the propagating direction to satisfy the divergence-free constraint. This means we want to approximate our solution, our Maxwell vector field solution, using only 2p plane waves that are Maxwell, that are solution of that have amplitude vector orthogonal to the propagation. The first thing we can do is to use a simplest version and apply the result from Helmholtz. We know that our vector field, our Maxwell vector field, we can take the curl of our Maxwell vector field and it's still Maxwell. So is also Helmholtz in each component. So we can approximate using Helmholtz vector plane waves with the estimate we have seen in the part for Helmholtz. Now, if this parameter j, the index of the Sobolev norm, is bigger or equal than 1, we can apply the curl and we reduce the order of the Sobolev norm. This is the bad step, the non-sharp step, because we expect for the Maxwell problem to have more or less the same approximation properties for u and curl u. And here, when we take the curl, we decrease by 1 the order of the Sobolev norm. So it means it's like if you were taking all the gradient of u, but actually we are only taking a curl. And now we use the Maxwell equation, so we rewrite the curl as omega squared u, and we see that the curl of Helmholtz vector plane waves are still plane waves, but now are divergence free, so are Maxwell plane waves. This gives approximation estimate by Maxwell plane waves, but in this case the order is not sharp because of this step. Okay. Yes, but the non-lazy is takes some time. No, is yes. We have only the H. We only have an H estimate for generalized polynomials using some using vector spherical harmonics to define the generalized harmonic vector generalized harmonic polynomials, and a special result by Verfurth that improves the Brembo-Hilbert theorem. But this is only H, and for the approximation by plane waves, we have to use a special Jacobi-Unger that preserves the Maxwell properties. When we multiply the plane wave by an amplitude vector that is orthogonal to the propagation direction, we want to obtain only generalized harmonic polynomials that are Maxwell generalized polynomials that are divergence free, and so this is the estimate the special Jacobi-Unger we need. Thank you.
There's a short question.
Okay. Essentially, this is a result in approximation theory. How well can you approximate with plane waves? And what is really remarkable is that in 2D, it turns out that you can approximate with plane waves better than you can approximate with polynomials. Because with polynomials, there is a Mergelian theorem that gives you exactly exponential convergence. And here you have faster than exponential, I mean p-convergence.
Faster than exponential when you are approximating a function, a generalized polynomial.
Oh, yes.
A function that,
yes.
If you have a nice function, yes, you can approximate
Yes, but
very
what
fast.
is interesting is that the results for polynomials have been obtained using completely different methodology, namely complex potential theory. And there are some interesting features, like the contamination principle, that the result is optimal, but it breaks down at the boundary very, very rapidly, and I wonder whether there is something similar happening here.
But is very sensitive to the behavior at the boundary. If your solution can be extended out of your domain, then you have exponential convergence, and the speed of the exponential depends on the distance from the singularity to the boundary of your domain. In 2D, you have to use this conformal distance and this complex analysis. In 3D, no, you don't have all this tool, because in 2D is a complex analysis, and 3D there is this result by Bagby, Boss, and Lemberg that are using subharmonic functions and this stuff, but it's very complicated and doesn't give anything explicit.
Okay, so we stop here. We thank you again.